Hi everyone! In today's video we will be covering our Chapter 4 material, which revolves around the idea of measures of variability. To kick off our conversation about measures of variability, we first need to define this term. In this case, variability refers to the extent to which data points in a dataset differ from each other and from the central tendency of that dataset. So if you'll recall from Chapter 3, we discussed the idea of measures of central tendency. In other words, the mean, median, and mode. And those three types of statistics allow us to describe the center point of a particular data set. Where measures of variability differ is now we will be talking about measures of how spread out or dispersed our values are. In addition to the measures of central tendency that we learned about in Chapter 3, to get a more holistic view of our data set and our distribution, we also have to take a look at the spread or the variability of the data points. And so let's take a look at the example depicted here on the right. As always, let's first take a look at our title to see what we're looking at. We have response times for two different ambulance services. So I have service A and service B. My y-axis is depicting frequency, or how many observations are we looking at in terms of these calls, and our x-axis is showing us the response time measured in minutes. So as our title here indicates, we are actually looking at two different services that have the same average response time, meaning that both of them have an average response of 7 minutes. However, we do see some variability in terms of how long it takes these services to respond. Service A, for example, has a lot more clustering around the mean, meaning there is less spread and less variability. So we could expect that the majority of calls for service by service A are going to be responded to between 4 and about 10 minutes. Okay, that's where the majority of our data points are here. Whereas with service B, even though they are also having an average, again represented here by X bar, of a response time of 7 minutes, we can see that sometimes they are responding a lot more quickly than service A because they have some frequency here between the 0 and 2 minute threshold, but they're also a little bit slower sometimes as well, where it can take them upwards of 12 to 14 minutes. So not only is it important for us to understand the average or those middle points, but we also have to understand the other aspects of our distribution as well. And one way that we can go about that is by calculating various measures of variability. And today we'll be talking about the range, the interquartile range, variance, and standard deviation. So let's start off by discussing the range. And the range is simply the distance between the highest and the lowest scores of a data set. The calculation revolves right around that very thing. All you have to do is take that highest score and subtract it by the lowest score. So let's say that I was interested in knowing what the range of the number of complaints that have been filed against police officers in St. Charles County in the last year. All that I have to do is take my highest value, which was 5 complaints filed against one officer, and subtract that by my lowest value, which was 0 complaints, to get a total score range of 5. And that's all you have to do. Again, just that highest value subtracted by the lowest value. The interquartile range, which is also referred to as the IQR, is a measure of statistical dispersion or variability that is used to describe the spread of the middle 50% of the data set. So with this particular measure, we are not necessarily concerned with the high end of our distribution or the low end over here. It's only this 50% that's highlighted in green here. How we go about this is first we have to identify, as the name indicates, our quartiles, which are separated into 25% chunks of our entire distribution of our data set. And the first thing we need to do is identify quartile 1, which is the median of the lower half of the data set. Secondly, we need to identify quartile 3, which is the median of the upper half of the data set. So let's take a look at how we would actually calculate this. To calculate the IQR, we need to put the numbers of the dataset in numerical order. And to get the IQR, we simply need to take quartile 3 minus quartile 1. And in order to figure that out, all we have to do is take n, which is the number of observations we'll have in a data set, so that'll depend on the context of the question that's being asked, and multiply that by 0.25, which is again indicating that first quartile, or Q1. And second, for Q3, or quartile 3, we take that same n value, which again is our total number of observations, and multiply that by 0.75 to get us that third quartile. If the numbers are not whole, then Q1 and Q3 are between two numbers. So we'll take a look at that in just a moment here. So to work through an example of this, let's take a look at an example of a sample in which I asked respondents to tell me how many traffic citations have you received within the last year. I've already ordered these for you, so we have a range from 0 to 10, and I asked 23 people. Remember that our capital N in this case is telling us the total number of observations that we have within the context of this problem. So again, I surveyed 23 people. To identify what Q1 is, I need to take N, which in this case is 23, so how many people did I ask, times 0.25 to get to quartile 1. Because 23 is an odd number, I already know that I'm not going to receive a whole number as my response here. So in this case, I have to look at both my fifth and sixth observation to figure out what my quartile is. That's what I have circled here in red. So I looked at the difference between my fifth and sixth observation and took the average of that. So very similar to the same idea that if we had an even number for our median, that we would take that average of those two numbers in between. And so that's where I'm getting this 0.5 value here, is I simply added 0 plus 1 and divided by 2 to get that 0.5. To get to quartile 3, I follow the exact same idea where I take my n value of 23, but this time I'm going to multiply it by my 75th observation value, so 0.75 to get to Q3. And again, since I have an odd number for my total number of observations, I am not going to receive a whole number for this, and so I have to look in between my 17th and 18th observation. In this case, both my 17th and 18th observation are both 3, which means that both of these respondents received 3 traffic citations within the last year. And so that's where I get my Q1 and my Q3 value. To actually calculate that range, though, there's one last step that we have to do, and that's taking our Q3 value and subtracting it by our Q1 value. So this is our last step of this calculation down here. And so, taking my Q3 value of 3 traffic citations and subtracting that by my Q1 value, which was half a citation, I get an interquartile range, or an IQR, of 2.5 citations in this past year. Remember, that's only within the context of this example in this particular sample, but that's a way to show you the average spread of that middle 50%. So again, I'm not necessarily taking into consideration all the people who got 0 traffic citations, or those that were much more extreme values that had quite an issue with having traffic citations in this range. I'm only really concerned with this middle 50%. So that's another way that I can measure the spread of a particular data set. There are a few disadvantages of using both the range and the IQR to describe the overall variability of a sample or a distribution. Some of the ones that have to do with the range include its sensitivity to outliers. In this case, recall that our formula for the range is only including that highest observation and subtracting that by the lowest observation within a particular sample or a distribution. And because of that, it can make it less representative of the overall spread of the data. If you recall from our last lecture video about Chapter 3 and the measures of central tendency, we talked about how the mean or the average value can oftentimes be really highly influenced by extreme values and outliers. Let's take that example that we used in terms of net worth from last lecture video. When we added Jeffrey Bezos to our sample, the average net worth increased of that sample by billions and billions of dollars. And so it didn't necessarily make it representative of what the true sample's net worth was, because it was being pulled in one direction. Kind of the same idea here with the range. If we were to include Jeffrey Bezos and his overall net worth, the range would encompass his net worth of about $168 billion, and it would go all the way down to what the lowest net worth was. But that doesn't show that our sample and the majority of those data points were clustered at that lower end of the distribution. Not everyone within our sample was billionaires, but again, the range doesn't account for that. It also ignores the overall data distribution because it's only using those minimum and maximum values. Therefore, it doesn't provide any information about the shape of the distribution or any of those measures of central tendency. In terms of the IQR, it's also not sensitive to all data points because, again, with the IQR, we are only concerned with that middle 50% of the data. Therefore, we are ignoring that uppermost quartile and the lowermost quartile. We also have this idea of data trimming, which is by focusing on that central 50% of the data, we could possibly be overlooking patterns and trends that may be occurring on either end of those extreme distributions. There also are a couple similarities between these disadvantages, so let's talk about those in terms of both the IQR and the range. Both of these statistics do not use all of the observations in their distribution. Again, the range is only concerned with that high and low number, and the IQR is only concerned with that 50th percentile in the middle of our distribution. One other important thing to note is that relative to our measures of central tendency, in this case our mean and median, both the range and IQR do not give us any information about how spread out our other data points are relative to that mean, average, or median values. And because of that, they might not be the best indicators for us to overall use in terms of looking at the variability of a distribution. There are two different types of statistics that actually account for a lot of the disadvantages of both the range and the IQR, and that is the variance and standard deviation. Whereas the range and IQR only account for a certain portion of our overall distribution, the variance and standard deviation use all of the observations that we have within a distribution. And because it uses all of those data points, we are able to measure how far away we are from the mean. And so this is bringing together our conversations from Chapter 3 with measures of central tendency, and now bringing that into a more holistic idea with our measures of variability to get the best picture we can of our distribution as a whole. Lastly, our variance and standard deviation increase in value as the distribution of scores become more diverse, and because of that, they can tell us what that spread or overall variability actually is. Before we begin our discussion about variance, it's first important to understand what a deviation actually is. And in this case, it's the difference between an individual data point and the mean. I know we've talked about up to this point that the mean is signified by an X bar, but just know that both of these symbols are interchangeable and they mean the same thing. Deviations are used to assess how much a particular observation deviates from that average value, and the way that we can calculate that is by taking the value of an individual observation and just subtracting it by the average value of the overall distribution. So, in very layman's simple terms, a deviation is simply the distance between an individual data point and the mean. So let's say, for example, if I scored an 85 on a statistics class test and the mean or the average score of the class was 80, my deviation would be 5 or 5 points, because all I would have to do is take my score of 85, subtract that from the class average of 80 to get 5 points. Let's say that you scored a 75 on the statistics exam, but the average still remains an 80. Your deviation in that case would be -5 because you deviate 5 points lower than the mean. We can calculate deviations for every single observation in a data set, and these deviations serve as the foundation for variance and standard deviation. The variance is a measure of dispersion or spread of the overall set of data points, and it quantifies how much each individual data point in a data set differs from the mean in the data set. The variance tells us how much the scores deviate from the mean on average. But because deviations can be positive or negative, as we just saw with our class example, you can either be above average on an exam or below average, we need to square these scores in order to avoid those canceling out. So, in other words, let's say that I was interested in figuring out the deviation between me and another student. One, I scored an 85 and the other student scored a 75, but that class average is still 80. If we took both of our scores, added them up, and divided, we would be right on average, right? Because I scored 5 points above average and they scored 5 points below average. But in this case, if we square both of those values, it takes away the negative symbol from the individual that scored lower. And so in other words, we're still able to measure that overall variance from our mean, but in a way that makes quantifiable sense to us and just doesn't cancel out each other's scores simply because one's positive and one's negative. I know that this formula can seem a little bit daunting, but we're going to break it down step by step. So let's first start off with this S2 symbol. This stands for variance, and so that's what we're calculating here with our formula below. Our very first step in calculating a variance is to subtract the mean from each individual observation. And so this section of the formula here is exactly what you saw on the last slide about deviations. So again, you just take what your individual score was or an individual observation within a data set and subtract it by that average. So again, sometimes you see mean by X bar, but in the conversations about measures of variability, we're going to keep with our Y bar language for now. The second step, as we alluded to, was to square each of these differences. Again, what this allows us to do is for those folks that would have scored lower than average on a statistics class, that their variability still counts, and it's not just being canceled out by someone that scored 5 points lower and 5 points higher to get that average. Once we square each of those differences, and that's what we have listed right here, we can go ahead and add up all of these totals together. This symbol here is sigma, which simply means to add them all up. So we're going to add together all of the observations that we have, subtracted by our average or mean value, Y bar, and squaring them. Once we've completed step 3, we are then going to divide our entire numerator, so this entire section up here, by our overall observations. So we're bringing back our language about capital N, which again just shows us the total number of observations within our data set, and we subtract that by 1. The reason for this capital N, again, is to show that overall group. So let's say in that particular class, it wasn't only me and that other student, but we had 10 of us total. In that case, I would be subtracting 10 minus 1 to get 9 for our bottom denominator figure here. But it would depend obviously on what all those other scores are as well. This is another way that we can mathematically approach the calculation of a variance, but I think it is far more confusing than the formula that we see above. But just know that if you see this in your textbook, that this is another way to approach calculating the variance. And so if it is helpful for you, go ahead and feel free to use this. It'll get you to the exact same answer. But for now, we're going to just focus on the main concept that variance tells us how far, on average, the data points are from the mean. Using the variance to describe the overall variability and spread of a data set or distribution is quite helpful. However, the interpretation of it can be quite difficult because it is expressed in squared units. And because of that, we typically use this idea of the standard deviation, which is simply taking the square root of the variance. And so in this case, the standard deviation is a measure of the amount of variation of the values around its mean. So very similar idea to the variance itself. However, By using the standard deviation, it helps our interpretation quite a bit because we are no longer using squared units, but just normal units. So if you take a look at the last slide, you'd notice that the variance formula is what we're solving for s squared. All that we're changing here for standard deviation is this symbol right here. And so instead of solving for the variance equals s squared, now we're just taking the square root of the exact same formula we just did to calculate the variance, but to calculate the standard deviation. So all we're doing here is adding in step 5. A low standard deviation indicates that the values tend to be close to the mean of the data set, and so they're all clustered in our center point. A high standard deviation indicates that the values are spread wide around the distribution, so they're not necessarily clustered around the mean. Similar to our same idea of the variance, there is another way that you can go about calculating the standard deviation. That's listed here on the bottom. Again, it's going to give you the exact same result as if you were to use the formula above. And so if this is helpful for you, you will see it within your textbook, and so feel free to use it. But again, I think these steps above are a lot more straightforward. So for the purposes of these videos, we will only be covering the above formula, but just know there's a ton of ways you can get there mathematically. Okay, so I know that is a lot of information to take in. This is probably a brand new concept to you in terms of the deviations, variance, and then standardizing that deviation. In this case, you might be asking yourself, why is this relevant to criminology and criminal justice, or even social science in general? Well, in this case, let's work through an example to see how calculating a standard deviation can be helpful for us in terms of ensuring equitable outcomes in our criminal justice system. So let's take a look at an example of sentencing outcomes. When someone is convicted of a crime, they are subsequently sentenced to prison. What we're looking at here on the right is a theoretical construction of what one judge may sentence 5 different defendants to. But again, you might be asking yourself, why do we need to calculate a standard deviation for sentence lengths? In this case, a small standard deviation would mean that this judge is very consistent in terms of their sentencing, meaning that most people are getting similar sentences to one another. But a large standard deviation would suggest that this judge's sentencing decisions are a lot more variable, meaning that some defendants get really short sentences and some defendants get really long sentences. But why does that actually matter? Well, in the criminal justice system and criminology as a whole, we want to ensure fairness and consistency within our sentencing outcomes. So, in this case, if one judge has a much higher standard deviation than others, it might suggest that there's some inconsistency or potential bias happening. And so we can use that as researchers to go and look at potential disparities. Also, within the realm of policy evaluation, lawmakers might look at sentencing variability to assess whether or not sentencing guidelines in and of themselves are effective. So if you've ever heard about sentencing guidelines before, that's the idea that the state legislature will tell a judge what range of months or years they have to be able to sentence someone for a particular crime. But if judges are straying away too much from those guidelines, that's important information for policymakers to know as well. So in the grand scheme of things, it's important for us to understand how fairly and consistently people are being treated, and if there is too much of a deviation, then we can identify that statistically and do something about it. So let's walk through this example of how to calculate the standard deviation for these 5 different sentence lengths. The very first step that we need to do in order to calculate a standard deviation is to find the mean, or the average amount of years that this particular judge, Judge Knudsen, is sentencing individuals to prison. In this case, if I add together all of my observations, so I'm just taking these values here, and then divide by 5, because we're only dealing with 5 individuals, I get an average sentence length of 4 years. Once we determine what the mean is for our data set, our first step in calculating the standard deviation is to subtract that mean value from each individual observation. I find it quite helpful to use this table method, and so if that's helpful for you, I highly encourage you to use that from now on. So let's work through this again together. Let's take Adam, for instance. Judge Knudsen sentenced him to 2 years, but we know that our average value was 4. And so because Adam only received 2 years, he deviated 2 years below Judge Knudsen's average sentence length. Same idea here for Beth. She only received 1 year sentence, and because of that, she has a deviation of -3. She had 3 years less than Judge Knudsen's average. But let's take a look at both Courtney and Edward here, because both of their individual observations are above our mean value. Because of that, they are deviating above Judge Knudsen's average of 4 years. So Courtney is 2 years above, because again, she got sentenced to 6. And David is 6 years above, because he got sentenced to 10 years, which is 6 years above Judge Knudsen's average sentence length of 4. And lastly, with Edward, he also received 1 year, and so his is going to match Beth's right here. So they are going to have the same deviation from the mean, which is 3 years less than Judge Knudsen's average. Once we calculate the deviation from the mean, we need to square each of these differences. The reason we do that, again, think back to our conversation about how the variance formula actually works, is if we didn't account for squaring these, all of these numbers would cancel each other out because I have some that are positive and I have some that are negative. But if I square each of these values, even my negative numbers become positive. And so we're able to measure that overall deviation in a way that makes more sense to us, right? Because we're not canceling out these figures from one another. So that's our next step. Once we calculate all of the deviations squared, our third step is to add together all of these values. And so this should look very familiar to us from step 2. Once I calculate all of these, all I'm doing is adding these values here to get a grand total of 62. Our fourth step is then to divide by the number of observations in our sample minus 1. In this case, remember that that is our n. We have 5 individuals in this case that are accounting for our different sentences. And so if I subtract that by 1, I get 4, and 62 divided by 4 is 15.5. And our very last step for calculating the standard deviation is simply taking the square root. But if I were to ask you to just calculate the variance of these different sentence lengths, you would stop right here at step 4, and your variance would be 15.5. However, if you recall, our variance is measured in s squared. So that means our outcome and variable is also measured in squared units. But that can make our interpretation really wonky and not make a whole lot of sense within context, because in this case, that would mean we are interpreting it within years squared, which doesn't make a whole lot of sense. By doing this last step, we're able to get rid of that problem and just get rid of that square by taking the square root to get a total of 3.937. And by having this result, we're now able to interpret that within the context of the problem. And so recall that Judge Knudsen's average sentence length was 4 years. And this means he deviates from that average in units of 3.937 years. So we would be able to measure, and this will come into play in our very next chapter with the normal distribution, just how different some of his outcomes may be. We have now standardized those units. In other words, if he were to sentence someone to 30 years in prison, that would be a huge deviation away from that mean. But in the context of just chapter 4, I'd just like you to calculate this value, but the interpretation of that will make a whole lot more sense when we get into our next chapter about the normal distribution and hypothesis testing. Lastly here, this is an example of how to use that alternative formula to calculate the standard deviation. Again, I do not expect you to use this, but if it is more helpful for you, you would get the exact same result as if we were to do that table method. Again, a lot of different ways to do the math here. So if it is helpful for you, feel free to use it. If not, feel free to skip this slide. Okay, let's talk about what happens to a standard deviation if something happens to the average value. So in this case, let's look at a scenario in which Missouri's Congress decided that the average punishment in the state wasn't harsh enough. And because of that, they wanted to add an additional 2 more years onto every sentence. And so we want to see how this affects both our average sentence length for Judge Knutson and that standard deviation. So in this case, what we're looking at in this table, the original table is right here. So just our person and our old sentence. And here's what it looks like if we are to add those additional 2 years to every sentence here below for all of our defendants. In this case, same steps as before. The very first thing we need to do to understand the standard deviation is to first calculate the new mean sentence. And in this case, if I just add all of these numbers up together and divide by 5, again, that is my n value, or how many observations I have as a whole, and I have 5 people, so that's where I'm getting that value. I get 6. 6 years is my new mean sentence length. Well, now that you've seen what the result is, you can also take a look at how that affects our original mean sentence length. Instead of actually adding together all of these, the relationship between a mean and a new potential mean, if we are to just add or subtract a value to it, you can just do that to the original mean, because each of these individual sentence lengths are increasing uniformly, meaning that they're each going up by 2. And so our average sentence length will also only go up 2 years. Okay, so I've gone ahead and done the math for us here using our alternative formula, just so that you could see it all on one slide. So on the last slide, we determined that our new mean sentence length was 6 years. So everything increased by a uniform value of 2. So our old sentence went from 2 to 4, 1 to 3, so on and so forth. And that means that our mean or average sentence length also increased by a value of 2. However, you may have started to notice that our standard deviation is the exact same value that we had before we even added these 2 additional years. The reason that this occurs is because adding or subtracting a constant, and in this case our constant is just that additional 2 years, shifts all of our values equally. And because of this, it doesn't affect the spread of the distribution. Let's take a look at how this actually plays out. All right, what we're looking at on the left here is our old sentence histogram. So all I've done is charted each of these sentence lengths for each individual. And so in this case, we had 2 individuals that were sentenced to 1 year. We had 1 individual that was sentenced to 2 years, so on and so forth. So our mean average, that original one for Judge Knutson, was 4 years. If you take a look here, here's what our new histogram looks like with the average sentence length of 6 years. These histograms are essentially identical in manner, and the only thing that is shifted here is my x-axis. So take a look at what that looks like here. On the left, I start with that first value of the 1 year sentence length. What I start with here is at the 3rd year, because each individual sentence increased by a factor of 2. We added those 2 years. And so because of that, my x-axis just essentially shifted by 2 years. But the spread or the variability remains exactly the same. And so the standard deviation does not change as a result. Because of this, I actually didn't even need to do the math calculation I did on the previous slide. Because of that relationship between the standard deviation, it is not affected by either adding or subtracting a value to those original data points. But let's take a look at an example that's a little bit different than what we dealt with the first time. So let's say in this case that Missouri's Congress changed their mind again, and they want to go back to the old sentence lengths, but instead, this time they want to rescale everything in months. So instead of expressing it in 2 years, you're going to get 24 months. What does this mean now for our average and our standard deviation? So what I'm looking at here is our original chart again. So we're back to the very first one. So we're not adding those 2 additional years from the previous example. This is our original data here in the second column. And if we are rescaling everything into months, we are multiplying everything by a factor of 12. 12 months in a year. So basically the sentence lengths they're going to be exactly the same, but Missouri's Congress just got weird and they said everything has to be in months now instead of years. So that's where I'm getting all these values. So 1 year is now 12 months, 6 years is now 72 months, so on and so forth. And so what does that mean for our average? Well, if you recall from our original example, our mean value of sentence length was 4 years. If we do 4 times 12, we get 48 months, which is what I'm looking at here. If you wanted to do the math yourself, feel free to do so. You would simply add these 5 values together and divide by 5, because again, I have 5 defendants that we're working with here. But that's where I get that 48-month total. So our mean didn't change in this case, it was just rescaled from years to months. So keeping in mind what our new mean is, which in this case again is 48 months, which is the same thing as 4 years, we're just scaling it differently. You may have noticed, and if we do the math here on my standard deviation, that the standard deviation has increased also by a factor of 12. And so why is that? I think it's helpful for us to take a look at this again in the context of our histogram. And so in this example, recall that our average sentence length is 4 years, and we're simply rescaling this to be in months rather than years. So everything here is increasing by a factor of 12. We didn't even really need to do the math on this, but if it's helpful for you, feel free to go ahead and do it if it helps you work it out. How does this affect, though, our x-axis? This is the central differentiating point between our first example of Missouri's Congress adding 2 years to every single person's sentence versus simply rescaling this to another unit. In this case, again, because all we're doing is changing the factor, it's the same amount of information just expressed differently, we need to account for that in our standard deviation as well. And so you can go ahead and do the math again on these standard deviations, but save yourself some time and just multiply this by the same factor we are doing with our mean above to go from our original standard deviation of 3.937. If I multiply that by 12, I get our new standard deviation of 47.244. The reason why the standard deviation changes in this example and not the first is because multiplying the standard deviation stretches the spread. All that we did in example 1 is shift it. Remember, with that x-axis, everything just increased by 2 years. And so the spread didn't change. But here, take a look at how our x-axis is scaled differently in months versus our original one in years. Our standard deviation has to increase by that same factor. If it didn't, it wouldn't make sense for us to express our average number of sentences in months when the standard deviation is still expressed in years. We have to make sure that they're both looking at the exact same thing and interpret those accordingly. As we wrap up here, I wanted to just briefly look at this table in terms of our relationship between our measures of variability and our levels of measurement. And so both our range and IQR are going to be the exact same here. You cannot calculate the range or an IQR for a nominal level variable. Think back to chapter 1 about what nominal level variables are. Again, they're ones that don't have a numerical attachment to them. They're oftentimes yes/no questions, or we did an example about whether you're a cat or a dog person. And so there's not a way for us to calculate a range or an IQR with non-numeric values. But you can do that for both ordinal and interval ratio level variables. In terms of the variance and standard deviation, since there is no numerical attachment to any nominal level variable, you can also not calculate it for anything there. Oftentimes we do not do that for ordinal level variables, but we can with interval ratio, because again, there is that numerical attachment and we know the unit difference in between each of those variables as well. Okay, so you've made it to the last slide of our chapter 4 video. So as with all of the previous chapters, now would be a good time to check in with yourself and see whether or not you can answer and articulate the following questions and bullet points listed below. In this case, with measures of variability, can you define and calculate a range, an IQR, a variance, and a standard deviation? and also understand how that operates if we rescale our calculations for our standard deviations. So those last two examples we just went through. What happens if I add or subtract a value from my original mean and observations? And what happens if I multiply or divide and essentially rescale my values? Know how those two things operate differently from one another and be able to articulate that as well. Remember, there isn't a whole lot of calculation that goes into this latter bullet point here, right? Because all we're doing is either adding by a factor or multiplying by a factor. And whether or not the standard deviation is affected depends on whether you're adding or subtracting or multiplying and dividing. So keep that in mind and understand the difference between the two. As always, if you have any questions, please feel free to email me or stop by my office hours, and I look forward to seeing you in the next video.